Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the programs on 8086 microprocessor. Today we will see few programs related to code converters. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals, authors A.K. Ray and K.M. Gurchandi, publication Tata Microelectronics. So first program we will see is write an ALP to convert packed BCD number to unpacked BCD number. So before going to the program, we will see what is by packed BCD and unpacked BCD. So BCD number means binary coded decimal where the allowed values are from 0 to 9. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for representation of the maximum number, that is 9, we require 4 bits. If each digit of BCD represent with 4 bits, it is called as packed BCD. Whereas in unpacked BCD, each digit of BCD represented with 8 bits. That will call as unpacked BCD. So now we are going to take one BCD number that we are going to be convert into unpacked BCD. So the example we are going to take in this program is 46H. Now we will see how to convert this 46H into unpacked BCD. Now when you write the 46, that is 46H in hexadecimal, the 6 is represented as 0, 1, 1, 0. We are allocating 4 bits. 4 will be taken as 0, 1, 0, 0. This is 4 bits. So this will call as packed BCD number. Now we want to convert this one into unpacked BCD. That means each BCD number we are going to be representing with 8 bits. That is 0, 0, 0, 0, 0, 1, 1, 0. So the output of this one we have to get as 0, 6H. Whereas 0, 1, 1, 0 we have to represent as 0, 0, 0, 0, 0, 1, 0, 0. That is 0, 4H. So now the output we are expecting is 0, 4 and 0, 6. So the 46H, which is an input which is in the packed BCD, that we are going to be converted into unpacked BCD as 0, 4, 0, 6H. This is the what output we are going to be expecting. So in the program, first we are going to be taken a data segment, where this data segment we are going to be load the BCD number which you want to convert. After conversion, we are going to be load that data into the memory. So we require a data segment. So the assembler assigned the data segment address. We have to load into data segment register by using the instruction move AX comma data followed by move DS comma AX. So here this data will consist of the address of the data segment assigned by the assembler will be loaded into DS. So first we have to load into AX, from AX to DS we have to load. As immediate data loading into segment register is not allowed in 8086 Then move AL comma BCD number. So this BCD number is there in the data segment. So in this example, we are taking the BCD number as 46H. So this will be loaded into AL. So AL will get 46H. Then move AH comma AL. So we are taking one more copy into AH register. Next, add AL register contains 0FH. The purpose of adding with 0FH is, so for retrieving the equivalent value from the 46, first we have to clear the upper 4 bits, then we have to retain the lower 4 bits. So for getting 06 from 46H, we have to AND with 0FH. So whenever any bit AND with 0, we are going to be get the output as 0. Any bit AND with 1, it is going to be use the result as the same bit. Now in our case, we have to clear the lower 4 bits and we have to retain the upper 4 bits. So the lower 4 bits we are going to be AND with zeros, whereas the upper 4 bits we are going to be AND with ones. So what is the value we are having is 46H. So 46 means 0, 1, 0, 0. 6 means 0, 1, 1, 0. So when you AND this 0 AND with 1, you will get 0, 1 AND with 1, 1, 1 AND with 1, 1, 0 AND with 1, 0, 0 AND with 0, 0, 0 AND with 0, 0, 1 AND with 0, 0, 0 AND with 0, 0. So now which you are going to get as 0, 4H. So for that we are going to use AND AL comma 04H. So after executing this instruction, the AL register content is equivalent to 04H. What is the BCD number we are considering is 46H. That we are going to be loaded into AH also. So AH also will have 46. Next we are doing AND AH comma F0H. So the second data, that is for getting 04, first we will retain the 4 bits, then we will clear the upper 4 bits. So now the value which you are going to get is 40H. So now we will shift these contents towards right side by 4 bit, then we are going to get the value as 04H. So this we will do by shift right. So first we will AND AH comma F0H. So when you AND with F0H, the AH contents is equivalent to F0. Now we want to shift this AH contents towards right side by 4 bits. So that count we are going to be loaded into CL register. So move CL comma 04H. Now we are going to shift the contents of AH register towards right side by 4 number of bits. So before shift operation, AH content is 40H. So after shift operation, the AH contents will become 04H. So how we will get this one is 40H. 40H equivalent is 01, 00, 00, 00. This is the equivalent of 40H. So for the first shift, each and every bit we are going to be shift towards right side by 1 bit. So this 0 will be placed here, this 1 will get here, this 0 will be get here, this 0, 0, 0, 0. The new insert value is 0. This is after first shift. After second shift, next this 0 will be placed here, this 0, then 1, then 0, 0, 0, this 0 will be placed here. This is after second shift, the inserted value is 0. Next, the third shift. During the third shift, what is the value you are going to have is this 0 will be placed here, 0, this 0 will be moved here, this 1 will be moved here, 0, 0, this 0. The new insert value is 0. Next, after fourth shift, this 0 will be placed to the right side, 0, 0, 0, 1, 0, 0. The new insert value is 0. Now the equivalent value you are going to get as 0, 0, 1, 0, 0, which is equivalent is 04H. So after shifting this data, we are going to get 04H. So the data which you are going to be considered as the packed BCD, we are considered as 46H. After operation, AL will have 06H, AH will have 04H. Now the combination of these two registers will use as unpacked BCD number. After shifting this contents of AH towards right side by 4 bits, we are going to get AH content is equivalent to 04H. Now we will fetch the address of unpacked BCD number in the data segment by using the move di comma offset direct to ubcd underscore number. So this is a variable name which you are given. So for this variable name, whatever the offset value is there, that we are going to be fetched to be loaded into DI register. So here this unpacked BCD is consist in the AX register. This AX register contents we are going to be loaded into the memory location which is pointed by the DA register. So to terminate the program and to return the DOS, we are going to execute int21h and the subroutine we are going to be called by moving into AH4CH. Now we will see the entire program at a glance. Assume CS colon code comma DS colon data. This is for requesting the assembler for code segment as well as data segment to allocate some memory. Next, to start the segment, we use the directive, segment directive. As it is belongs to data, we are going to proceed this one with data. So whatever you are placed between segment to NS, this will be belongs to a particular segment. In this example, it is data segment. So in this data segment, we are going to be have two variables. One is BCD number. The second one is unpacked BCD number. So the input which you are going to be consider is a packed BCD, which is 8-bit of size. The value which you are allocating for this one is 46H. After conversion, the unpacked BCD, we are going to be reserved one memory location, which is of 16-bit size. So we will take DW. As it is uninitialized, you will get a question mark. DUP indicates it is for reserving the memory. So after conversion, the unpacked BCD, we are going to be loaded into this memory location. Next, we will move to the code segment. So in the code segment, the starting of the segment will have segment directive. As it is a code segment, it is preceded with code segment. Start. So first we will load the data segment address assigned by the assembler into the DS register. So for that we will write the instructions are move dx comma x comma data, move ds comma ax. Next, for fetching the BCD number into AL register, so move AL comma BCD number. Then we have retrieving, that is a lower 4 bits and upper 4 bits. So we are going to take two registers. One is in AL and the one is in AH by move AH comma AL. Next, AND AL comma 04H. So when you AND AL contents with the 04H, the lower 4 bits will be retained, the upper 4 bits will be cleared. Next, AND AH comma F0H. So when you AND AH contents with F0H, the upper 4 bits will be retained and the lower 4 bits will be cleared. So for shifting the upper 4 bits to the lower 4 bits, then we use move CL comma 04H. This is for placing the count, how many times we want to shift the contents of AH register. Now to make the upper nibble to lower nibble, we want to shift these contents by 4 bits. So we move that CL register with the 04H, shift the contents of AH register with 4 bits. Then we will fetch the address of unpacked BCD number in the data segment by using the offset directive. That offset value will be loaded into the DI register by using the instruction move DI comma offset of unpacked BCD number. Into this memory location, we want to move the contents of unpacked BCD which is exist in the AX register by using the instruction move in square braces DI comma AX. So now the AX register contains the unpacked BCD number. This register contents will be loaded into the memory location which is pointed by DI. To return to the DOS, we are going to execute int21h by calling the subroutine at 4ch will be loaded into AH register. So move AH comma 4ch int21h. Now we can end the code segment by using the segment directive, that is end-dash directive. As it is for a code segment, so code end-dash. To end the program, we will use end, where the program is started with the label start, that we are going to be end. This is the program for conversion of packed BCD number into unpacked BCD. Next, we will say packed BCD number to ASCII number. So write an ALP to convert a packed BCD number into ASCII number. So in this, the input is taken as a packed BCD. The output we are expecting is the ASCII equivalent of packed BCD number. So in this example, we are taking as 46H as packed BCD number. This we are going to be convert into ASCII. So the ASCII value which we want to fetch is 34 and 36H. So the procedure for converting the packed BCD into ASCII number is, first we will convert the packed BCD number into unpacked BCD number. Whatever the unpacked BCD number which we got, so for that we are going to add 3030H. When you add with the 3030H, the result which is going to be produced is a ASCII number for the given packed BCD number. The various instructions which we are going to use for converting packed BCD into ASCII numbers are, so first we are taking the data in the data segment. So we are going to be load the data segment address into the data segment which is assigned by the assembler by using a two instructions move AH comma data followed by move DS comma AX. So this instruction will load the data segment address into the data segment register. Then the BCD number, that is packed BCD number, which we want to convert into ASCII. First we will load into AL as well as in AH register by using the instruction move AL comma packed BCD, that is packed BCD number, and move AH comma AL. So now here AL content is 46H as well as AH content is also 46H. Then we will add AL comma 04H. So after executing this instruction, AL contents will become 06H. Then add AH comma F0H. So when you add with F0H, AH contents, the upper 4 bits will be retained, the lower 4 bits will be cleared. So we are going to get this one as 40H. Then for shifting the upper nibble to lower nibble, we will shift the contents towards right side by 4 bits by loading the count, that is CL register with 04H, then you go for shifting. So after shifting, the AH contents is equivalent to 04H. Now the AH register content is 04, AL content is 06, that you can take as AX register is consist of 04, 0X. So for converting this number into ASCII, we are going to add with 3030H. Either you can go for addition or you can do bit by bit OR operation. So if I go for OR operation, A ORed with 1, it is going to produce the value as 1. A ORed with 0, it is going to give the number itself. So in this one, we have a 0 value in the upper 4 bits, in the next case lower 4 bits, again upper 4 bits, lower 4 bits. So as you are adding ORing with the 0, the result is going to be retained the same number. So 6 ORing with 0 will give us as 0. 0 ORing with 3 is going to produce 3. 4 ORed with 0 will give us 4. 0 ORed with 3 it is going to produce 34. So after ORing H contents with 3030H, the AX contents will produce the value as 3436H, which is the equivalent of 04 and 06H. Now this converted ASCII number we want to load into the memory. So for that, first we will fetch the address by using the instruction move DA comma offset of ASCII number. So this instruction will fetch the offset value of the ASCII number in the data segment that will be loaded into the DI register. So into this memory location, AH contents which is holding the ASCII number will be loaded by using the instruction move in square braces DA comma AX. Now we will terminate the program by calling int21H with the subroutine at 4CH to return to the DOS. So for that, move AH comma 4CH followed by int21H. This is the program for converting packed BCD number into ASCII number. Now we will see the entire program at a glance. Assume CS colon code comma DS colon data. This is for using the assume directive requesting the assembler for assigning the memory for code segment and data segment. In the data segment, we are going to be declare two variables. One is BCD number. The second one is ASCII number. BCD number, it is a input which is of 8 bits. So we will use DB defined by the value which it is going to be assigned is 46H. ASCII number, just we are reserving the memory. So for that we are going to use DUP. We are requesting only one memory location. That memory is of 16 bit size. Question mark it indicates it is uninitialized. Then we will end the data segment by using the end dash directive as it is belongs to the data segment. It is preceded by data. Now we will start the code segment by using the segment directive as it is belongs to code segment start. So first we will load the data segment address into the DS register by using move AX comma data followed by move DS comma AX. Then the BCD number that will be loaded into AL as well as AH by using the instruction move AL comma BCD number move AH comma AL. Then for retrieving the lower 4 bits of AL contents and AL comma 04H. For retrieving upper 4 bits of AH register and AH comma F0H. This upper nibble to move to the lower nibble, we will shift this contents towards right side by 4 bits. So for that we will load the number of shift operations into CL register by using move CL comma 04H. Then we will give shift operation towards right SHR AH contents towards right side by 4 bits which are specified in CL register. Next, the unpacked BCD number which is there in the AX register, that will be odd with a 30 to generate the ASCII equivalent of unpacked BCD which is in AX register. Now the AX register which is holding the ASCII number, that we are going to be loaded into the memory by fetching the address of ASCII number in the data segment by using the assembler directive offset directive. This will fetch us the offset value of ASCII number in the data segment that will be loaded into DI register by using the move DI comma offset of ASCII number. Into this memory location, we want to move the ASCII number which is existing in AX register contents. So we use the instruction move in square braces DI comma AX. So the ASCII number will be loaded into memory location. Then we trace the interrupt 21H by using I into 21H by calling the subroutine for CH that will be loaded into AH. So these two instructions were written to the DOS prompt. Then we have to end the code segment by using the end dash directive. As this segment belongs to code segment, we are going to be proceed with this one with code. To end the program, we use the directive end. The program is started with the label start. Now, the next program we will see for converting unpacked BCD number into packed BCD number. Write an ALP to convert unpacked BCD to packed BCD number. So, in this case, we will take the unpacked BCD number, that is 0406. This is input, and the output which you are going to be expect is 46H. So, how we can do this? So, AL will consist of 06H, AH will consist of 04H. Now this 04H will be shifted towards left side by 4 bits. Either you can go for shift towards left side or rotate without carry. So in that case, you will get this value as 40H after shift operation. Then add AL register with AH register. That is 06 will be added with 40. Then we are going to get the output is 46H, where you are restricting the number of bits assigned for each BCD number is only 4 bits. Now this is what the expected output, which we will call as a packed BCD format. Now we will see the program. First, the data segment address assigned by the assembler, we have to load into the data segment register by using move AX comma data followed by move DS comma AX. As the immediate data loading directly into the data segment is not allowed, first we will load into AX register, from AX register to DS. Then move the unpacked BCD number into AX register. This unpacked BCD number is declared in the data segment that will be loaded into AX. Now out of this AX register contents, AL will be written as it is, whereas AH contents we are going to be shift towards left side by 4 bits. So for that, we are going to load 04H into the CL register. Then we are going to be shift these contents towards left side by 4 bits. That is SHL, AH comma CL. Either we can go for rotating towards left side by 4 bits, or we can go for shift towards left side. So either you can use SHL instruction or you can use ROL instruction. Then we will or the content of AH register with AL register. Now AL register will hold the unpacked BCD number converted into the packed BCD. So this AL register we want to load into the memory. So for that, first we will fetch the address of the packed BCD number by using the offset directive into the DI register by using move DI comma offset of BCD number. So now into this memory location, we want to load the AL register which is packed BCD number of the given unpacked BCD. So for that we use the instruction move in square braces DI comma AL. So the AL will consist of the packed BCD number that will be loaded into the memory location which is pointed by DI. Then we will terminate the program by calling int21h. For returning to the DOS, we will call the subroutine at 4ch that will be loaded into AH. So move AH comma 4ch int21h. Now we will see the entire program at a glance. Assume CS colon code comma DS colon data. So this is assume directive is used for requesting the assembler for assigning the memory for code and data segment. To start the data segment, we use the segment directive. As it is related to data, we will be preceded by data. So data segment. In this, we are declaring two variables. One is unpacked BCD number. The second one is packed BCD number. Unpacked BCD number is the input which is of 16-bit size. The value which you are going to be assigned is 0406H. So after conversion into packed BCD, that we are going to be loaded into the memory. So it is to reserve the memory by using that the UP assembler directive. As it is uninitialized, question mark will be there. How many data we are going to have is only one memory data. One memory is required which is of 8-bit size. Now we will end this data segment by using the end dash directive. As it is corresponding to the data, we will be precede this one with data end dash. Now we will start the code segment by using the segment directive. As it is related to code segment, we will precede this one with code. So code segment start move AX comma data, move DS comma AX. These two instructions for loading the data segment address assigned by the assembler into the data segment register. As immediate data loading into the data segment register is not allowed, so we will move the data assigned segment address assigned by the assembler into AX from AX to DS. Then fetch the unpacked BCD number into AX by using the instruction move AH comma unpacked BCD number. Now we want to shift the upper 4 bits towards left side by 4 bits. So for that we will place move CL comma 04H. Now this AH contents we are going to be shift towards left side by using the instruction SHL AH comma CL. So this instruction will shift the contents towards left side by 4 bits. Then they are going to be OR the AL register contents with AH register contents. So when you OR this one, we are going to get the packed BCD number into the AL register. So this AL register contents we are going to be loaded into the memory location whose memory address is loaded with offset of the packed BCD number. Then we will terminate the program by using the int21h. To return to the DOS prompt, we are going to have the subroutine at 4ch that will be loaded into AH. Then we will write int21h. Then we will end the code segment by using code endes. And to end the program, we use the directive end directive where the program is started with the label is start. Next program is for writing an ALP to convert ASCII number to packed BCD number. So here the input is the ASCII number we are taking as 3436H. So the output which you are going to be expect is which is a packed BCD number. The output is 46H. So for converting this, first we will take the ASCII number that is 3436H. So from this we will subtract 3030. Then we are going to get 0406H. Now this is a unpacked BCD. From this unpacked BCD, we are going to be retain the lower that is AL register content as this, where AH contents will shift the contents towards right side, left side by 4 bits. Then you will get 40H. Then we are going to add either you can do logical or AND operation, addition operation. 6 plus 0 will get as 6. 0 odd with 4 will get as 46, which is nothing but the output which we require. For this, we will write the program by loading the data segment address into the DS register by using the equation, that is instructions move AX comma data as well as move DS comma AX. So these two instructions will load the data segment address assigned by the assembler into the data segment register. Then we will load the ASCII number that is input into the AX register by using move AX comma ASCII number. Then we are going to subtract AH contents with 3030H. So now here AX content is 3436. After doing the subtraction with the 3030, AX contents will become 0406. Then we want to shift the upper 4 bits of AH contents to the lower 4 bits. Lower 4 bits to upper 4 bits. So for that we will write move CL comma 04H. Now here AH content is 04H. This we want to shift towards left side by 4 bits. So for that we will write SHL AH comma CL. Now AH contents will be shifted towards left side by 4 bits. Now we will get the output as 40H. Now this is what the H register contains. Now RAL comma AH. So AL content is 06H. AH content is 40H. So when you add this one, so 0 RN with any bit will give the same bit. Similarly, 0 odd with 4 will use 46H. This is the packed BCD which is there in the AL. So now this AL register contents will move into the memory location. So for fetching the address of the memory location of packed BCD number, we use the offset directive. So offset directive will fetch us the offset value of BCD number. This memory will be loaded into DI register. So into this memory location, we want to load the BCD number which is existing in the AL. So for that we use the instruction move in square braces BA comma AL. So now the AL contains which is a packed BCD number that will be loaded into the memory which is pointed by DI register. Then we will terminate the program by using INT21H. For returning to the DOS, we execute the subroutine 4CH by loading into AH register. So move AH comma 4CH followed by INT21H. Now we will see the entire program at a glance. Assume CS colon code comma DS colon data. Data segment. ASCII number is 16-bit size. So that is defined word. The value which you are going to be storing is 3436H. Then BCD number which is of 8 bit after conversion. It require one memory location of 8 bits. It is reserving the memory with uninitialized. Then we will end the data segment by using data NS. To start the code segment, we will use the directive segment. As it is code segment, we will precede this one with code. Code segment. Start of the program with the start label. Move AX comma data, move DS comma AX. So these two instructions are used for loading the data segment address into the DS. As immediate data loading into the segment register is not allowed, first we load into AX register. From AX register to segment register we are going to load. Then fetching the input which is a ASCII number into AH register by using the instruction move AX comma ASCII number. Subtract 3030 from AX for retrieving the unpacked BCD number. Then we have to rotate or shift the AH contents towards left side by 4 bits. So for that we will load the count move CL comma 04H. Now shift the contents towards left side by using SHL instruction AH comma 04H. Either we can use SHL instruction or we can also use ROR instruction or ROL instruction. All are valid. Then are the content of AL and HS AH. So for getting the packed BCD number in AL register. Now we will load this packed BCD number into the memory location. So first we will fetch the address of the BCD number in the data segment by using the offset directive into the DI register using move DI comma offset of BCD number. So once we fetch this address into this memory location, we are going to be load the output which is there in the AL register. That packed BCD number which is in AL register will be moved into the memory location. To terminate the program, we execute INT21H interrupts by calling to the return to the DOS prompt subroutine at 4CH that will be loaded into AH register. Move AH comma 4CH INT21H. Then we will end the code segment by using code NS. To end the program, we use the directive end. As the program is started at the label start, so we will end this program with start label. Next, we will see write an ALP to convert hexadecimal number to ASCII value. So hexadecimal number means for BCD number the allowed values are only 0 to 9, whereas for hexadecimal number from 0 to 9, after that we are going to have A to H. So for converting into ASCII value, first we will convert the given hexa value into valid BCD number then we are going to be convert into ASCII. So what is invalid BCD numbers are if hexadecimal is present from A to H, A to F, A to F, that we are going to be convert into valid BCD number. So whenever the digit is more than 9, we are going to be at 06 for it. So we'll write the instructions move AX comma data followed by move DS comma AX. These instructions are for loading the data segment address assigned by the assembler into the data segment register. Then for fetching the address of hexadecimal series. So now instead of converting a single hexadecimal number, here we are going to take a series of hexadecimal number that we are going to be converted into a series of ASCII numbers. So move AX comma SI offset of hexadecimal number. So to point to the first data of the hexadecimal number that we are going to be load into SI register. Next, for pointing to the ASCII number memory, so we are going to be load this address into DI register. So move DI comma offset of ASCII series. Then how many values, that is how many hexadecimal numbers are present here, that we are going to be load into CX register by using the instruction move CX comma count. As each and every digit is of 8-bit size, so we are going to be take the first data which is pointed by SI register to the hexadecimal number will be loaded into AL register. Move AL comma in square braces of SI. So in the first iteration, the first hexadecimal number will be loaded into AL register. After that, second number, third number, like this. In each iteration, one hexadecimal number will be loaded into AL register. This AL register contents we are going to be compared with 0H. So if AL content is lies between 0 to 9, then we are not going to get it is a valid BCD number. If it is lies between A to F, then it is a invalid BCD number that we want to convert into valid BCD. So we will compare with the 0H. So when the number of AL register is greater than 0AH, then the carry flag is equivalent to 1. So which indicates it is a valid number, no need to add anything. So we can skip off. Then you can convert that one into ASCII number. Suppose if this number is greater than 9, then in that case you get carry flag is equivalent to 0. So when you do this carry flag is equivalent to 0, it indicates it is a invalid number. Then we go for converting this number by adding +6 for it. So move compare AL comma 0AH, then JC L1, which is for comparing the carry flag. After comparing AL with 0AH, if any carry is generated, then we are going to be skipped to L1, where we are doing the conversion of BCD number into ASCII. Suppose if this number is invalid number, then we are going to add 07 to AL for converting into hexadecimal 06. So this is for converting the invalid BCD number into valid BCD number. Then we are going to add 30. So once this number is converted into ASCII, the AL register contents will be loaded into the memory location which is pointed by DI. So what is DI is consist of? DI is consist of the offset of the ASCII numbers. So after converting, this number will be loaded here. Its equivalent value. Then for fetching the next memory location, we will first decrement the count. That is decrement CH. For pointing to the next memory location, for the source data, increment SI. For the destination data, increment DI. As one data comparison is done, so we are going to be decrement this count. So if CX content is 0, what indicate is all numbers are done. All conversions are done. So we can exit the program. Suppose if CX content is non-zero, still conversion is there. Conversion should take place for further numbers. So when CX content is equivalent to 0, here the jet flag is equivalent to 1. When Cx is non-zero, jet flag is equivalent to 0. So when jet flag is equivalent to 0, it indicates still conversion should be take place. So again we go for retrieving the data. So for that we will check JNZ L2. So if the Cx contents are non-zero, go to label 2. Where we have placed this label 2? Label 2 is placed for fetching the data. Once the Cx content is 0, that means all the conversion is done, then we can terminate the program by raising INT21H by calling the subroutine at 4CH into AH register for returning to the DOS by using the instruction move AH,04H INT21H. Now we will see the entire program at a glance. Assume CS colon code, DS colon data. This is for requesting the assembler for reserving the memory for code segment and data segment. To start the segment, we use the directive segment directive. As it is corresponding to the data, we will proceed this one with data segment. This example, we are considering XR numbers as a series of numbers which is of 8 bits, that is defined by. Then how many values we are going to be have here? 1, 2, 3, 4 numbers. So we are going to place 04 as count into count variable. Then after conversion, we are going to use the ASCII numbers which is of 8 bit size. How many values we are having? 04H, and to reserve the memory DUP question mark, it is for uninitialized. To end the data segment, we use data enders. Now we will start the code segment by using the segment directive proceed with code. Start of the code segment, start the first instruction to load the data segment address assigned by the assembler into DS register by using move AX, data followed by move DS, AX. For fetching the address of the input, that is series of numbers, into SR register, the target location, that is ASCII numbers, into the DI register. How many values we are going to be convert, that we are going to be load into CX register with the variable out. For fetching each and every number from the source data, so move AL, in square braces of SI, where SI will point to the hexadecimal number. Now we will compare this AL contents with 0 AH. So if this number which is present in the AL register is greater than 9, then we are going to get the carry flag is equivalent to 0. If it is less than 9, that is equivalent to 9, then the carry flag is equivalent to 1. So when it is 1, we go for skipping the addition. Otherwise, we are going to add 06 for the AL register contents. Then for converting into the ASCII number, or AL contents with 30H. So now AL will consist of the ASCII number that we are going to be loaded into the memory location. For pointing to the advancing to the next memory location, increment SI, increment DI. As one conversion is done, we will decrement the count which is in the CX. So this loop will be iterated until CX is equivalent to 0. So JNZ loop 2. So loop 2 will be placed for fetching the data, that is here, move AL, SI. So once the CX content is 0, we can terminate the program by using move AH, 4CH followed by int 21H. Then we will end the code segment by using code enders. To end the program, we use the end directive with the start label. So in this session, we have discussed programs related for conversion, code conversion. We have done conversion from packed BCD to unpacked BCD, packed BCD to ASCII. Next, unpacked BCD to packed BCD, ASCII to packed BCD. Apart from that, hexadecimal to ASCII also we have done. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.